Okay, so today we'll start talking about Maxwell's equations. In particular, we're going to see Maxwell's equations in relativistic form. And in fact, I hope to finally write down the full equations for electrodynamics. But let's see how far we can get. So what have we done so far? Right? So we have shown from symmetries what type of, from Lorentz and Poincare symmetries, what type of particles we should expect. We should have, depending on whether it's massive or massless, what kind of spin it can have, and so on. And then we also have started looking at the field theory side of things. So we have looked at the Klein-Gordon equation, which I think I said before, eventually will give us spin zero particles when we quantize it. We have now looked at the Dirac equation, which is I partial slash, for now, I partial slash minus m psi equals to 0. This is a 4-component guy. And this is corresponding to the spin 1/2. And then we're now going to look at Maxwell's equations. Okay? And Maxwell's equations is going to look like the following. So I'm going to write it down, and then we will, in fact, talk about what it means as we go along. And oops, and this is spin 1. This is the spin 1. Actually, I should call this, and this is the 1, the massless spin 1. And that's where we're going. And then once I've written this down, I'm going to come back and modify this a little bit. Okay? But before we start with Maxwell's equations itself, I want to spend a little bit of time, maybe 10-20 minutes, talking about conservation laws. Okay? So what are conservation laws? By conservation laws, I mean the following. So let's start in the non-relativistic context. Yeah, let's start in the non-relativistic context. And let's just think about water for now. Okay, so that, let's say I have a tank of water. So, and in fact I should say local conservation laws. Conservation itself means something, is preserved, right? It doesn't change. That's what conserved means. But the local conservation law, we'll see, has a bit more to it than that, right? So it's called local because actually things can change locally, but basically whatever comes in must add to the local quantity that you are looking at. Or whatever is flowing out must take away from the local charge density or mass density. So let's start with water. So you have a tank of water, and you may have seen analogies like that from your multivariable calculus. Right? So say I have a hole, and I pump water in. Let's put a pipe here, and then I have water pump. Actually, they can come in and out whichever way we want. But let's say it's doing this, right? So what you may recall from your multivariable calculus is that the total amount of water per unit charge. So how much water, per unit time is flowing into or out of the tank. Okay, so into the tank would be from here, and basically what you need to do is you need to multiply the velocity of the water, which can flow in different directions, right? So let me make it bigger. So if you have an opening like that, and the water flow can take different directions throughout the area, then you should have learned in your multivariable calculus that the velocity darted into the area, where here the area is pointing into the water. So actually, let's do this, because the convention for multivariable calculus is that it's always pointing outwards. Right? So area is pointing outwards. This is the left channel. Okay, water is flowing in, but the area is pointing out. So I need to put in a minus sign because I want the net. Area. Net change in volume. Right? So this is actually the volume of water flowing into the tank per unit time. Right? This is something that you should have learned in your multivariable calculus course. Right? And so why is that so? Because you can think of this as I'm sorry, I need to integrate over the area. Okay, and why is that so? Because think of this as a little area. Look at a little segment here. Then the dot product between velocity and the area up to a sign is just how much length passes through the area per unit time, right? So this is actually how much length per unit time passing through that is the velocity dotted into the perpendicular. And then you multiply it by the magnitude of the area. But that means that length times area is in fact volume, right? And so that's what this means. And then if you integrate over the whole area, that tells you volume per time. Volume per time. Okay. Of course, you can also do it for, so this is a plus. So it will add d volume dt will be, will give you a positive contribution to the area, the left area, right? And then for the right area, it would be if the area is defined to be still outwards. Then v dot dA, in fact, will be the negative rate of change in the sense of volume, right? Because you're losing volume now. You're losing volume of water. So essentially, as long as your dA is pointing outwards, then no matter what the flow of the water is, the dot product will take care of the sign, right? And so in other words, the total rate of change of volume is in fact just the sum of the velocities integrated over the area of all the possible channels going in and out of the tank. Okay, so this is something that I hope you've seen in multivariable calculus. But when you learn it in multivariable calculus, you don't care about relativity, right? So I'm going to. This is purely in the non-relativistic setup, and what I'm assuming here is that also for simplicity, the density of water is fixed. So I can think of this as basically proportional. This is proportional to the total mass, right? If density of water is constant, right? Which I'll assume because just for simplicity, okay. If you want to include the density of water, then the total mass, so if rho were not constant, then what you will do is instead dm dt will now be minus, and then it will be rho v dot dA, okay, over the areas. Why is it rho v? Because just like v dot dA is the length passing through per unit time, rho times v dot dA will be the total amount of length per, mass per unit. So rho is, remember, mass per unit volume, and then if you multiply it by the length, basically you're asking the mass per unit area passing through this area, right? So again, it's mass per unit area passing through, let me just write it down, rho v dot dA would be the mass per area per time times dA times the magnitude of the area. And so that's why when you integrate over all the areas will cancel and you get mass per unit time. Okay? And so we can work with either one. Maybe since I wrote it down, I'll deal with this one. And now you can shrink this tank to as small as you want, and you realize that basically the total mass, remember, is just total total mass is just the integral of the charge density or the mass density inside the tank. And so dm dt, of course, is just rho dot integrated over the volume. And we have figured out that however is changing, the total rate of change must be due to the flow, either in or out, which means it's minus rho v dA. Okay. And as you know, you can use Gauss's theorem. Remember that this is flux. and the total flux is just equal to the divergence of rho dV over the volume. And like I said, we can consider this volume to be anything we want. So in particular, I can shrink this tank to as small as I want. And once it gets very, very small, I can just drop the integral sign. Okay. Every time I teach, you're going to hear me complain about markers. I don't like markers. I wish they would have one classroom with, at least one classroom with chalkboard. Right? Yeah. So I can't erase this thing. Okay, so let's try a different marker. What's happening? So let me write this again. I have used Gauss's theorem. Maybe I'll write it down here. So this is Gauss's theorem. To say that a flow, which is most easily understood as the velocity times the density dotted over the area, that's the easiest to understand geometrically. But through Gauss's theorem, you can express the time rate of change of density integrated over volume to be the same as the same volume integral, but now with the negative divergence of rho v. Okay. So the only thing I've assumed is that this is non-relativistic. Okay, but because this is any volume, so any volume, therefore it has to hold even if the volume is infinitesimal. And so now we see that there's a law that we can write down. Rho dot must be equals to minus divergence of rho v. Okay. And if I move it to the left-hand side, this will be dt rho plus d partial I. This is derivative with respect to x of rho of x v. Okay, so both rho and v depends on where you are. So I need to differentiate both with respect to x. This is equals to 0. Okay, so again, remember this is the flow in or out of an infinitesimal volume, because now to be able to go from here to here, I shrunk the volume down to an infinitesimal one, infinitesimal volume. That's how you should think about Gauss's theorem, right? Gauss's theorem tells you that basically flow is divergence. That's what you should remember. And then on the left-hand side, since when you have flow, if whatever substance you care about is conserved, then it must obey this kind of conservation, where what flows in will increase the mass. What flows out will decrease the mass. If I don't care about conservation, then I wouldn't even have an equation like that, right? So what flows in increases the mass. What flows out decreases the mass. Okay. Otherwise, it's not called conservation. So this is what local conservation means. It's not that the quantity doesn't change. It's that in a small volume, doesn't matter how small it is, as long as there's something going in, it will increase that quantity, and if there's something flowing out, it will decrease the quantity. Right? It's very intuitive at the non-relativistic level. What is slightly less intuitive is that this is not quite correct because of relativity. Right? And so one of the reasons you can think about, one thing you can think about is that of length contraction. Right? So mass is not really a Lorentz invariant because you can or rather mass density is not Lorentz invariant because of length contraction, right? So if you boost to a different thing, the mass density at a given point would transform because of the length contraction. What you measure to be length in one frame is not the same length that you measure in some other frame. You have to be very careful what you mean by length, in fact. So what you do is you want to, so this is non-relativistic, okay? But the relativistic version is easy to write down once you know the non-relativistic version. That's why I always begin with the non-relativistic one. So for the relativistic one, instead of having just a sequential velocity, you now promote this to a four velocity of the fluid. For us, it's water, right? But you know, it's a fluid. And so that's all you really need. You just want to make sure that the velocity is now Lorentz covariant, which means you take into account things like time dilation, length contraction, and stuff like that. Then what you have is instead you define a forecurrent, which is in fact rho times V mu. Okay, rho times V mu. Then this whole thing you treat it as a 4 vector, which is a 4 vector under Lorentz transformations. And then this is a guy that obeys this equation, but once I write it down, you will see that it is Lorentz covariant. Right? So this is Lorentz covariant because now I promoted my V to a 4 vector. And now with this, which means that is d0 dt of rho V0, right? Previously this was just 1, but it's not true anymore because there's a difference between proper time and the coordinate time. The global time and proper time is different. Proper time of the one packet of the fluid is not the same as the global Cartesian time, because if you're moving, your proper time is different. And then this is the x of rho Vi. Okay, so this looks very much like this term, but this term now has a V0. But now with this notation, you can just write it as partial mu, J mu. Okay, and now if you know how this guy, the partial derivative transform with Lorentz transformations, and if you make sure that your V is a proper velocity, then this will also transform properly, and then with the contraction of the indices, this is now a Lorentz scalar. So when I say that this is 0, right, that was 0. So now all I did was promote the 0 component to V0. So this is a Lorentz scalar. And it is a scalar because it's local, right? It's an infinitesimal volume of water. And there's something flowing in, there's something flowing out, and that changes the total rate of change. That changes the total amount of fluid in this little packet, right? And that's what this expresses, the local conservation law in a Lorentz invariant way. Okay, so this guy is always what we mean. When I tell you, okay, we have something conserved, then locally, then this is what you should think of. You should think of what is the J, right? So of course, depending on the situation, the J will be different. But if it's something that's locally conserved, then this is in fact this is in fact what we mean, right? This is local conservation. Yeah. So not only conserved, but also consistent with relativity. That's basically the point. We've seen this before. I always at this point have to ask because I think it's not familiar, right? This is why I do this. We've seen this before. 1, 2, well, you've taken my class before. Well, that guy has seen my GR class. Well, you have, good. Okay, I know what you know. Good. Okay, so but only half the class at most. So yeah, definitely should talk about this. And this is important because if you remember on the right-hand side of Maxwell's equations, if you remember, I actually wrote down a J. And in fact, it's not a coincidence. That J will be the electric current. So let me just tell you, the prime example that we're going to do is that of electric charge. So instead of thinking about water or fluid, you should think about it as an electric current, right? So maybe you have a resistor or whatever electrical circuit here, and you have electrons going through the circuit. And this, in fact, would be the local conservation law for the electric current. Right? So J mu is the electric current. What it will mean is that if you're in a rest frame, right? So in the rest frame, rho will correspond to the electric charge density, right? So this is the electric charge density in the rest frame of the current. So something is flowing, right? But if you flow with the current, at the instant where you're at rest with the current, you will measure the electric charge density to be rho. And V is just the proper velocity of the current measured with respect to some, we're assuming there's some inertial frame, right? And so V is the one is the velocity measured with respect to that frame. Okay. So it takes the same form, but of course, depending on the situation, you have to make sure you understand what exactly is rho, what exactly is V. The meaning is different, but the form is the same thing. Okay. So with that, then I can now return to Maxwell's equations. Yes.
I'm just curious.
Yeah.
So is it the non-relativistic and the relativistic current is the same? Is it?
Yeah. So remember, there's no V naught here, right? So V naught. I'm assuming that V naught. So the last way to think about it is a point particle. With a point particle, charge density would just be m, and then times dx mu momentum. Sorry, d tau. Okay, this is the momentum of a one point particle. Let's say 1 point particle of the fluid, for example, right? In the non-relativistic limit, proper time, tau is proper time, will be almost the same as time, coordinate time. X0 is coordinate time. So then, in the non-relativistic limit, you get m, and then you get dt essentially, and you get 1. And then the spatial components, this will be roughly t, it will be roughly dx dt. Okay, but this is in the non-relativistic limit. But if you don't, if it is relativistic, then you have to use this expression, right? To get a coordinate, to get a Lorentz invariant, Lorentz covariant for momentum. a different perspective to how things work. Any questions so far?
So in 2D
Yeah.
space, the B field will look like a dipole in 3 dimensions. In 3 dimensions.
What do you mean, dipole? You mean generated by what? It has to be generated by something still, right?
I
So,
mean, in 2D space, we only have one component B field.
yes, yes.
And in Y
So it's not a vector in particular, right? So,
yeah.
yeah. So what are you thinking about?
I think it like maybe a vertex in 2D space.
Vortex?
Yeah.
But what do you mean by that? It's a vector field? Or?
Yeah, it's a.
Yeah, then it cannot be a B field, right? Right, this is not a scalar. Yeah. Yeah. Okay, anyway, so any more questions?
Yes.
Yeah.
So why is in 2D the Lebesgue only has 2 index?
So that only, remember the Lebesgue is defined as the symbol that is fully antisymmetric.
Yeah.
So it has to have the same number of indices as you have the number of dimensions, because it's fully antisymmetric. If you have too many, then it will be identically 0. So there's a maximum number that you can have. Yeah. Yeah. So you cannot have more than 2 in particular, in 2 dimensions. So you cannot construct a fully antisymmetric guy and contract it with this guy to give you a vector. It's not possible. Yeah. No fully antisymmetric object can have more indices than the number of dimensions, because it will be 0, right? So just if that's not clear, just try to do that. Let's say you have 3 indices, I, J, K, and you antisymmetrize it in 2D. Well, let's figure this out. Remember, all of them have to be distinct, right? So you have 0, 1, and then what? Right? Then the third one you are out of indices already.
Yeah.
Right? Yeah. Okay, let's take a 10-minute break, shall we? And then we'll come back and continue this discussion on Maxwell's equations. Start recording. So note, right, E and B are not Lorentz covariant. And that's not surprising. There's no 0th component to it. So what you do, and this might be a homework problem, what you do is, in fact, you start from the fact that this is a rank 2 tensor in Lorentzian space-time, right? So if you want to know what is f mu prime x prime, meaning you want to boost between the prime frame and the unprime frame, well, you know what to do. So if you now say that x alpha is lambda alpha beta dx, so x prime beta, then remember that tells you that the coordinates, the infinitesimal coordinates transform in this way. So then you see that basically this guy is just f alpha beta of x, but then you boost it, and then you contract these guys with the Lorentz transformation matrices. Okay? So if you want to change from one frame to the other, what you first do is work in terms of f mu, because f mu is a Lorentz covariant object. Right? So far we've done scalars, we've also done direct spinors. Direct spinors have their own special transformation groups. They don't look like that because it transforms under SL2C, 2 copies of SL2C. So that's a little bit special. But now we're back to just Lorentz tensor. So except now it's a rank 2 guy. So when you go from one frame to another frame, you have to contract 2 copies of the Lorentz transformation matrix to this guy to find out the transformation law. So inside this guy, we'll have the E and the B, right? Fi0 is the E and Fij is the B. But this guy will give you E prime and B prime. And by prime, I just mean the E and B field in this frame, in the X prime frame. Okay? And so E prime will not be equal to E, B prime will not be equal to B, but some mixture of the two, right? And so again, if you learn your electromagnetism well, you will know in fact that when you go between different frames, your E and B will in fact be mixed up relative to the E and B in other frames. Just like time and space is mixed up when you go between frames, right? Yeah, but again, for people who have never done any relativity, this might be something very, very new, very novel, right? Can be a little bit bizarre. In fact, there are some books that assume relativity from the outset, which I completely agree with, right? And they can show you, I don't know how many of you have seen this, that if you require that relativity is correct, you can show that if you have an electric field and you boost to a different frame, you must produce a magnetic field. Or vice versa, if you start with only a magnetic field and you boost to a different frame, you realize you must also have an electric field. So they cannot exist without each other. The relativity demands that E and B must coexist in the same theory. Right? This is something that is quite instructive to understand if you're learning electromagnetism, but it's not always taught. Okay? But anyway, so I think in your homework you're going to work a simple example out, transforming E and B between different frames. But because this is a field theory class, I want to now focus on what do these equations mean. Okay. So the first thing to do, because we're going to do quantity field theory, is to in fact start with a Bianchi identity. Okay. So in principle, you can take the F mu nu equations as it stands, and you can see it's a set of first order equations, and you can solve it. Right? In principle, you can. And in fact, a lot of what you do in your undergraduate electromagnetism course is in fact to solve the equations in this form. Right? You all the Stokes theorem, Gauss's theorem, Faraday's law, whatever. It all comes from these. I claim they all come from these equations. But actually, I won't do it here. I think it's a homework problem. So I'm going to resist doing it. So for homework, you're going to convert to curl E equations, divergence of E equations, and then you have a curl of B equations, and then divergence of B. Right? The divergence of B is easiest to remember. 0. Curl of E gives you rho. In this case, it will give you J0. Which is and then curl of B I think is minus E dot, right? And then curl of BE is B dot plus J vector. Right? And what you discover is that, so don't quote me on this because I always forget the signs, the relative signs, but in your homework, you will figure out how to go from these guys to these guys, so that you can see for yourself that I'm not pulling your leg, right? You really do have, this is in fact the Maxwell's equations that you're familiar with. Like I said, it's a scandal, I think. We have more than 100 years beyond Maxwell, right? I think this is maybe 150 years now. So we definitely should be teaching electromagnetism from the outset like that. But we don't. We still don't, right? Anyway, so for our QFD class instead, I want to begin with Bianchi because this will, in fact, introduce the notion of vector potentials. So it turns out to be something called the Poincare lemma. Okay, so what does the Poincare lemma say? It says the following. If you take the antisymmetric derivative of something that is antisymmetric already, so it doesn't matter how many indices it has. Okay, so if you have, let's call it H. Okay, so you got H, and it has a number of indices. Let's say alpha 1 to alpha n, then all fully antisymmetric. Okay. Then, what does the Poincare lemma say? It says if the antisymmetric derivative of this. So now, not only is this antisymmetric, I take the derivative such that everybody is antisymmetric. If this is 0, then alpha 1 to alpha n, h alpha 1 to alpha n itself is an antisymmetric derivative of something else. So let's call it G or K, okay? Alpha 1, alpha 2, alpha n. Okay? And in fact, it goes backwards as well. So it's if and only if, meaning if this is true, then this is true. And if this is true, of course this will be true. Right? Actually, this way is easy to see. Okay? The non-trivial part is this way, which is that if you have a volume of space-time where a fully antisymmetric object gives you 0 when you take its antisymmetric first derivative, then you can show that this object itself is the antisymmetric derivative of something else. Okay? But for us, it's very simple. So for us, for our situation, it's much simpler because now we have, so for Maxwell, for Bianchi, what do we have? We have a partial alpha f mu. This is 0. So what does that mean? The f mu, remember, is already fully antisymmetric. So now I have a first derivative of a fully antisymmetric object that is also 0. So now n is just 2, basically, i.e. n is just 2. Which means that f mu itself must just be itself an antisymmetric derivative of a one-index object. Okay, so from Bianchi, this is implied. Of course, you can ask, why don't we just start with A, right? And in fact, that's what quantum electrodynamics does. You basically just start with A. But I want to motivate it from something that is familiar, which is Maxwell's equations, right? So first, we promote Maxwell's equations to a relativistic notation. And then from the relativistic notation, we realize that the Bianchi identity implies that f mu, remember this is basically a composite object made of electric and magnetic fields. But all of that, because of the Bianchi identity, tells us that basically all of that is subsumed into the antisymmetric derivative of a vector potential. A mu is a vector, a space-time vector. And this is now going to contain all the information about f mu, because all you have to do is just take the derivative and you get f. Right? So a mu is called the vector potential and contains all the information regarding F mu nu, which means regarding E and B. Okay? And why? Because you just take the derivative and you get F mu nu. And so now you can show, now we've gotten rid of the Bianchi, because Bianchi, we realize, just tells you the existence of A, right? So basically we can say, all that Bianchi does is that it tells you use the vector potential. And in the quantum case, you realize that it's indispensable. If you want to construct a local quantum field theory, it turns out to be very, very difficult if you don't use A, right? I don't know whether you can prove that it's impossible, but basically it's for all practical purposes, right? No one has figured out how to do it. So you can do it in a non-local way, but at least locally you can't do it, okay, as far as I can tell. So that's Bianchi. But now you have Bianchi, you can now plug this in, okay, and you see that, what is this now? F partial mu. And remember, F mu nu is now the antisymmetric derivative of A, so mu nu minus nu mu equals to J nu, okay? And in particular, remember in the Dirac case and the Klein-Gordon case, we didn't have a source, right? This is the source of F mu nu. So in fact, let's think about, to consider source-free equations. Okay, so then what we have now is something simpler. Which is 0. Okay. So we have taken Maxwell's equations, which are these three equations here, and now we have reduced it all the way down to just one equation here. Okay, and actually this is where we should say a few words. Okay, the first thing is something called gauge invariance. And then we realize that once we realize gauge invariance, we realize that that equation cannot be solved as it stands. Okay, so let me write it down over here first. Yep.
What does the K here mean?
It just means the some object whose curl, this is basically a curl, a higher dimensional curl, gives you back H. That's all it means, right? So there's a way to construct it, but I won't do it here. But there is, but basically it's saying that from this n rank tensor, you can construct a K whose curl is H. Right? So something like that exists, but we're not going to construct it.
Okay, so does K have other spatial property?
Come again?
So does K have something spatial property?
Yeah, it's fully antisymmetric, just like H. But it has one less index. Yeah. Yeah. Any questions for me? Don't be shy.
How can we do the commutate? How can we commutate in the commutate the index when, I mean, for example, the derivative alpha of F mu nu, we have a commutator in the index, and how can we
Commute the index.
Yeah.
Say again, where did it show up?
Like
Like that?
the F mu nu.
Uh-huh.
Yeah.
So F mu nu, F alpha beta is partial alpha A beta minus partial beta A alpha. or if you write it downstairs, it will be partial alpha A beta minus partial beta A alpha.
That's what I mean, for the derivative of alpha of f mu mu,
Derivative of alpha at mu mu.
by alpha of f mu
You mean something like
mu.
this?
Yes, yes. How can we use the...
Yeah, so let's do it. Okay, let's check that. Let's check that this is actually 0. Okay, and you can tell me whether this answers your question. So firstly, this is the derivative of what? F alpha beta itself is the antisymmetric derivative of A. Okay. Now I want to further antisymmetrize this. Right? So after I do this, I antisymmetrize one more time. But if I really want to antisymmetrize everybody, then it's the same as basically saying that, well, it's just twice, because every time I have alpha beta, and antisymmetrize it, and then antisymmetrize it one more time, I just have twice of this. You see what I'm saying? So now it just amounts to antisymmetrizing it twice, which means I'll have 2. Okay? Or if you don't, it's just proportional to this, right? Because anyway, everybody is antisymmetric. So that's the first observation. Okay, and I write it this way because if you realize that this is proportional to the antisymmetric derivative, but now it's 2 derivatives acting on A, then remember that derivatives commute, right? Derivatives commute. So this has to be the same as, for example, this, right? Because I can just move my derivatives around all I want.
Yeah.
But I'm supposed to antisymmetrize this. So this is at the same time equals to minus partial mu partial alpha A beta. Why? Because I just swapped alpha beta, right? But it's also equals to itself because the derivatives commute.
Yeah.
So if something is equals to negative itself, it's 0.
Yeah.
So this is a example calculation of what it means to do this.
Yeah.
Does that help you?
Yeah.
Okay. I think you guys have a question.
You just confused about if you say that the K, the captain K is
Yeah.
the high dimensional curl.
Yeah.
Is this curl, the curl is linked to the curl effect or the...
Yeah, it is. So curl, I just used the word curl. I didn't want to get I don't want to throw too much math, but since you asked, curl in general, in fact, is this guy here. The curl that you are, so vector calculus curl, I claim is actually less general than what I'm doing here. So let's write it down first. Okay, so vector calculus curl, for example, you take the curl of A, right? And this is what you probably learned in sometime down your E&M class. You would be told, oh, the B field is the curl of A. So if you ask what's the I component of A, of the curl of A, you realize this is Levi beta I j k partial j a k with the sum over j and k. Okay, and this will be equal to b I. Okay, and what you realize is that if you actually write it out, if you compare it with the relativistic notation, you will realize that this is actually one of the Bianchi identities. Okay, and I'll let you discover it for yourself in your homework. Okay, this is one of the Bianchi identities. But the more general definition of curl is actually in terms of what I have been talking about, which is the derivative but fully antisymmetric derivative of an antisymmetric guy. So this guy must be antisymmetric. Either is one index, or if it has more than one index, it must be antisymmetric. And then you take the one derivative and make sure that all the indices are antisymmetrized. This is the definition of curl. Okay, so curl of H alpha 1 to alpha n is this guy. That's what it means. Okay, and so it's a definition. But I claim, so you might ask, right, how the heck is this related to that? Right? So what you realize is that if you take the curl of AI, the one index object AI, and don't worry about time. Okay, if you just work in space but not time, then the curl of AI will just be partial IAJ minus partial JAI. Right? That's what the definition says. Take your object, take one derivative, and antisymmetrize the derivative. Well, what is this? This is Fij. We just saw it. Right? But this is the magnetic field. This is, in fact, epsilon minus epsilon ijk bk. Sorry, I just did your homework for you. Okay, I'm going to stop here. But yeah, so I have this compulsion to just tell you everything. But I'm going to stop here. This is your homework problem, right? But you see that in fact curl is nothing but B, and that in fact sits with what you have learned. Have you seen this before? Curl of A is B. Have you seen it in your electromagnetic course? Yeah. So this is nothing but what I just said, except in a different language. Except that basically it's just where you put your Lagrangian, right? But once you go beyond vector calculus, sometimes your Lagrangian is not available. Meaning you don't have enough indices, or you have too few indices, or don't even care that you have a Lagrangian. So you can just let it be a standalone definition for curl. That's the point, right? It can serve, and that's why it's more general. It works whether or not you have a Lagrangian to use. Okay? Yeah. Did I make you happy? Or?
Yes.
Okay. Okay, good. Very good. Okay, so now, let's come back to what I was saying earlier, which is that with Bianchi, we realized that F mu nu is the curl, or the antisymmetric derivative of A. But now with that, we realize something. So there's an ambiguity in A, in the following sense. Okay, so classically, at least, it's F alpha beta that is measurable. Why? Because F alpha beta is what gives you the E and B fields. And it's the E and B fields that produces forces, right? And it's the forces that you can measure in the lab. You can measure the magnetic field, you can measure the electric field, but you can't measure A, because you have to take the derivative of A, then that gives you E and B, then you can measure it. So A alpha is not directly measurable. Okay. Quantum mechanically is a little more subtle, but let me just focus on the classical part first. Okay, it's more subtle because of one example why it's more subtle is because of something called the Aharonov-Bohm effect, right? But I'll talk about this later. Now, So what does that mean? It means that, at least at the classical level, A alpha, so let me just tell you, cannot be distinguished between A alpha plus a gradient, okay, which I think I call it, let me just call it a L, okay, lambda. Okay, so this L is just an arbitrary function. Cannot be distinguished. In other words, you cannot tell, you cannot, at least classically, you cannot distinguish, you cannot set up an experiment to tell the difference whether I have A alpha or A alpha plus a gradient. Right? This is just a gradient of a function, of an arbitrary function. Why is that so? Because, let's just plug it in. Let's just compare F mu mu built out of A versus F mu mu built out of A plus the gradient of lambda. Okay, let's calculate. So this is partial alpha A beta minus partial alpha beta A alpha. This guy is the sum of these two guys, so let's do it term by term. So this is the same, okay, but now I have lambda, so I need to do partial alpha, and then this is beta, so it will be partial beta lambda minus partial beta, and then this is alpha, so it will be partial alpha lambda, okay? And so this is an example of what we already did just now. I erased it already, which is that when you anti-symmetrize a double derivative on something, the double derivatives commute. So this will just cancel out, okay? And therefore you're back to F alpha beta of A. And that's why I say that A versus A plus a gradient is completely indistinguishable. You can't tell the difference. There's no measurement that you can make that will tell you is A this or that, right? Because what you can measure is is E and B, which is the F mu nu, and not A, right? Like I said, it's quantum mechanically, actually, it's basically the same as what the Aharonov-Bohm effect is. Do you guys know the Aharonov-Bohm effect? Aharonov-Bohm. Do you guys know? No? No? Who knows? Nobody. Okay, well, we're almost out of time, but give me 10 more minutes. I hope there's nobody after us, but I remember Yu Lao Shi has a meeting, right? Okay, anyway, let's talk a bit more until she keeps us up. So let's come back to our equations for A, right? So remember that we in free space without a source, we have basically partial mu F mu nu equals to partial mu F mu nu is now partial mu A nu minus partial mu A mu. And without a source, it's just this, okay? But because we have just realized that A and A plus a gradient gives you the same F mu nu, it comes to that basically whatever that solves this equation must also be solved if you just add a gradient, right? So if, let's just write it down, if A solves, let's call this star, so does A plus a gradient, right? So if I plug in A and it gives me 0, then I plug in A plus lambda, well, but gradient of lambda. But gradient of lambda will always cancel out anyway. So it will also solve this equation, right? It's a linear equation. So A plus now, so in other words, there's an infinite degree of ambiguity. That we have an equation that has this ambiguity. And how do we solve it? How do we pin it down, right? And so the way to do it is to, let me just give you the gist of it, and then we'll talk more the next time. The way to get out of this kind of stalemate is to choose a gauge. Okay, this sounds like just jargon, and it is, right? So choose a gauge just means that you impose some condition on a mu so that this Maxwell's equations become solvable. So I'll talk more about it the next time, but let me just show you that it works. Okay, so the most common gauge that is Lorentz invariant. Remember, we're doing electromagnetism, so we like to make sure that our equations are Lorentz invariant. But because of this gauge ambiguity, actually there's no, it's a little tricky. You can actually choose something that's not gauge Lorentz invariant, but we usually, for example, there's something called a Coulomb gauge, which is not gauge invariant. But if you do choose a gauge Lorentz invariant, sorry, the Coulomb gauge is not Lorentz invariant. But if you want to choose a Lorentz invariant gauge, a most common one is to just choose that the divergence of the vector potential is 0. Okay, so this is called the Lorentz gauge. I'm sorry, there's no T. So if you read Jackson, his book tells you that this poor guy Lorentz, just because his name has a 1 T less than this Lorentz, so we always mix it up. So it's Lorentz invariant, but the gauge is named after the guy without a T. Okay? I mean, choose your name properly. Okay, otherwise, yeah, you should be more famous. This guy is much less famous than this guy, unfortunately. But now, if you do that, let's just see that it works before I let you guys go. So let's expand this out. This is now partial mu, a nu. So you may recall this is nothing but a wave operator. Okay, minus now, these are partial derivatives, so I can commute them. Partial mu, a mu. Now, so now you see why I choose this gauge. Because this term is identically 0 if I make this choice, right? And this is now equal to 0. And so this just tells you that now I have 4 wave equations. Why 4? Because nu runs from 0 to 3. And this is actually just, in terms of solutions, this is just the massless limit of the Klein-Gordon equation, right? And so we know how to solve that, and therefore we also know how to solve this guy. Okay. So next time I'll show you more about this. Why this is a consistent thing to do, right? You might ask me, how do you know you didn't do something mathematically illegal? Maybe I did maybe by choosing this gauge, it breaks the equation somehow, right? So I have to show you that this is always a consistent choice. This is always the problem. When you choose a gauge, you should, in fact, always prove that your gauge is consistent. And in fact, with the Lorentz gauge, it's easy to see, and I'll do it the next time. And then we'll see how the photon emerges from this, right? So remember that I told you this is supposed to give you the massless spin 1. So I will answer this question the next time. How does massless spin 1 come out of this. Okay, and we'll see this next time. The classical, it's basically a classical limit of massless spin 1 come out of this. Okay, see you guys on Friday.